Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to find the empirical and molecular formulas of a given compound based on its combustion analysis. So let's get into this. So in this problem we're given lysine, an essential amino acid in the human body, and it contains carbon, hydrogen, oxygen, and nitrogen. So in this problem we're given two experiments. In one experiment, the complete combustion of 2.175 grams of lysine gives us 3.93 grams of carbon dioxide and 1.88 grams of water. In a separate experiment, we react 1.873 grams of lysine, and that gives us 0.435 grams of NH3. So then they're asking us, what is the empirical formula of lysine and what is the molecular formula from the data given? So your way of attacking this problem, or the method of solving this problem, is to convert the given grams of your substances, your products, to moles of the elements that are in the substance itself. Once you get moles of all the elements in the substance, you want to then set up a pseudo formula with those moles, get the smallest whole number ratio, and so on and so forth. So that's really what we want to do. We want to convert grams to moles and then use the moles to find the empirical formula. And so let's go ahead and start doing that. So they give us that 2.175 grams of lysine gives you 3.93 grams of carbon dioxide. So we want to convert carbon dioxide to carbon. All of the carbon in the carbon dioxide came from the lysine. So therefore, we can find the moles of carbon that were in the original amount. And so let's go ahead and start that. So we're given 3.93 grams of CO2. So we're going to convert that to moles of carbon. So we're going to use the molar mass of carbon dioxide, 44.01 grams of CO2. Let me double check that. Yep. And so we have 1 mole of CO2 on top. So the grams of CO2 cancel out. And now I can convert moles of CO2 to moles of carbon using the formula as a mole ratio. I know for every 1 molecule of CO2, I get 1 atom of carbon. So it's a 1-to-1 ratio. So that means that 1 mole of CO2 is going to give me 1 mole of carbon. So moles of carbon cancel out. So I can calculate the moles of carbon that came from the original sample, and I get 0.08929. Oops. Sorry about that. What did I get? 0.8929. So 0.8929 moles of carbon. And then I can do the same thing for water. So since my substance has hydrogen in it, then all of the hydrogen that ends up in the water came from my substance. So I'm going to convert that to moles of hydrogen. So then I take the 1.88, so 1.88 grams of water. I'm going to use the molar mass of water, which is like 18.02. Let me double check. Yep, 18.02. So we have 18.02 grams of water on the bottom, 1 mole of water on top. So grams cancels out. Now I have moles of water. I can use the formula to get my mole ratio. Every molecule of water gives me 2 atoms of hydrogen. So it's a 1-to-2 ratio. So it's the same with the mole ratio as well. So for every 1 mole of water, I put moles of water on the bottom, I get 2 moles of hydrogen. So moles of water cancel out. Now I can do the calculation. I get moles of hydrogen, and when I calculate that, I get 0.208. Oops. 0.208. 0.208657 moles of hydrogen. Okay, so as far as sig figs go, I have 3 sig figs here. So I should have 3 sig figs here. 1, 2, 3. So that's my last sig fig. I keep an extra one just in case for rounding mistakes. So again, I have 3 here. So I should end up having 3 because that's the least number. So 1, 2, 3. So this is underlined. And I have a few extra digits. You really just need to keep 1 extra digit because if you use this carry on, you don't want to have rounding errors and things like that. Okay, so now I have, excuse me, I have the moles of carbon, the moles of hydrogen. I would now need the moles of oxygen and the moles of nitrogen before I can go on to figure out what the empirical formula is. So you need to go to the second experiment. But before that, I need to know how much mass is left over for the oxygen and nitrogen. That's going to be important. So I need to convert these to masses of carbon and hydrogen using the molar mass of carbon and hydrogen. So when I do that, I'm going to use the molar mass of carbon as a conversion factor. So this is going to be, oops. So 1 mole of carbon on the bottom, and you got 12.011 grams of carbon on top. When that cancels out, you get 1.07255. 1.07255 grams of carbon. And if I do the same thing with hydrogen, I'm going to multiply this by its molar mass. So I put 1 mole of hydrogen on the bottom, and I put 1.008 grams of hydrogen on top. Moles of hydrogen cancel out, and when I calculate the mass, I get 0.210, 0.210 326 grams of hydrogen. Again, I have the least number is 3 sig figs, so I underline the 3rd sig fig there. Again, 3 sig figs, underline the 3rd sig fig there. Okay, so now I can subtract out the grams of carbon and hydrogen from the original amount of the lysine that I start with, and I'll have the mass of the the mass of the oxygen and the nitrogen that was left over from the experiment, or from the mass of the whole. So if I take 2.175 minus 1.07255 grams minus 0.210326 grams. And again, that's going to be my last sig fig. And when I subtract that out, I get 0.892, 0.892, 124. Now, when you're adding and subtracting, the answer should have the same number of decimal places as the least number of decimal places. So I have 3 decimal places here. I have 2 here. I have 3 here. Oops. Yep. I have 3 here. So 2 is the lesser amount of decimal places. So then that would be my last digit of significance. And so now that I have this is supposed to be the mass. This is grams. This is the mass of oxygen plus nitrogen. So if I could get these separated, I can then figure out what the moles of each of these are. And that's going to be my next step. Okay, so that means that we're going to have to go to the next experiment. So in the second experiment, they say they take 1.873 grams of lysine and they react it again and they tell us that it gives 0.435 grams of NH3. Well, we can find out what moles of nitrogen came from that amount of lysine. So let's go ahead and do that. So we got 1.873 grams, or we have, 0.435 grams. So we'll start with that. So 0.435 grams of NH3. And we got to keep in mind that all of the nitrogen in NH3 came from our original sample, our sample of lysine. So if we could figure out the moles that came from that sample, then that will help us to find the empirical formula. So all we need to do is convert this amount of grams of NH3 to moles of nitrogen. So we're going to use the molar mass of NH3, and that is 17.031. So 17.031 grams of NH3 on the bottom, 1 mole of NH3 on the top. So grams of NH3 cancel out. Now we have moles. Now we can use the mole ratio from the formula. So 1 molecule of NH3 gives me 1 atom of nitrogen. So it's a 1-to-1 ratio. So I can use that as a mole ratio. So I'm going to multiply by 1 mole of NH3 on the bottom, 1 mole of nitrogen on top. Moles of NH3 cancel out. Now I have moles of N. So then I can change that. Or actually, I can convert that to grams. And the reason I want to convert that to grams is because then I can subtract that from the original amount of my, well, not my lysine, but I'm gonna subtract it out from the mass that I have left over from here, right? But I have to do something first. So let's go ahead and find that. So we'll calculate the mass of nitrogen, and we're going to use the molar mass of nitrogen, which is, I believe, 14.01. Let me double check that. Close enough. So 14.007 grams of nitrogen over 1 mole of nitrogen. So moles cancels out, and then I get, what do I get? 0.3577. 0.357762 grams of nitrogen. Again, I'm starting with 3 sig figs here. I got 5 here. This is exact. I got 5 here. So the smallest number is 3. So I should only have 3 sig figs here. 1, 2, 3. But I'm keeping extra to avoid rounding mistakes. Okay, so this is the amount of grams that came from this amount of lysine. Now, the thing to keep in mind that's really important to solving this, and this is what makes this problem a little bit difficult, is you have to remember that this amount of nitrogen is proportional to a given amount of your lysine. So remember, no matter, I should say that there is a percent composition for your compound. So there's a certain percentage of lysine, the certain percentage of the mass of lysine is due to the nitrogen in the lysine. That percentage stays the same no matter how much you have. So, and percentage is just a fractional amount of the substance you have that you're comparing to the whole. What do I mean by that? Right, so a percentage is, so if I want to know the percent of nitrogen, I find the grams of nitrogen in my sample, I divide it by the total sample, multiply by 100, and I get the percent mass that's due to nitrogen in my sample. Well, all I'm doing is I'm taking the mass of nitrogen, dividing it by the mass of the whole of the sample, multiplying by 100. If I don't multiply by 100, I don't get the percentage, but I still get the fractional amount. And so here, I have the mass of nitrogen, and I have the mass of the original sample, so I have the fractional amount. The fractional amount of the element in a substance is always the same, no matter how much of the substance you have. So the reason this is important is because the original amount is what I'm working with regard to carbon dioxide and water. That's where I got the grams of carbon, the moles of carbon, the moles of hydrogen, and so on. So I need to go back to that sample. The fact that the fractional amount of nitrogen to the sample is always the same allows me to do that. So what I can do is I can set up the ratio here. So I know that that's 0.3. So 0.357762 grams of nitrogen over whatever the sample from which that amount of nitrogen came from, and that is 1.873. So 1.873 grams of the lysine. Well, that fraction is going to be equal to an X amount of grams, right? We don't need the grams there just yet. We got an X amount of nitrogen in grams for this sample, 2.175. So we could put 2.175 grams of lysine. So I have the gram amount from this sample, but I want the gram amount from this sample. Why? Because when I find the gram amount from this sample here, I can then subtract that gram amount from this here. So remember, we subtracted from our original amount here, 2.175, we subtracted the mass of the carbon and the mass of the hydrogen, and then we have this left over, which is oxygen and nitrogen. So if I can find the gram amount of the nitrogen in this sample of lysine, I can subtract that from this, and I'll have the mass of oxygen. So I'll have the mass of the nitrogen from this original sample, and I'll have the mass amount of the oxygen that's left over, and I can convert those to mole amounts using their molar masses. So when I solve this, when you solve for x, you cross multiply, and you solve for x. X is, what's x? 0.415, 0.415, where is it? 447. Oops, 447. 447 grams of nitrogen. So that is the amount of nitrogen in grams from my original sample of 2.175. So now I have grams, and I can convert that to moles using the molar mass of nitrogen. So if I use the molar mass of nitrogen, so here, that I can use same thing. It's 14.007 grams per mole. So since I have grams on the top here, I'm going to put 007 grams of nitrogen, 1 mole of nitrogen on the top. And so grams of nitrogen will cancel out. I get moles. And when I calculate that out, I get, where is it? 0.02965, 0.06925. Let me double check that. 0.02965. I butchered that. 2965. 2965 and 99. And so that's going to, let me write that down here. So that's going to be equal to 0.0296599 moles of nitrogen. Yeah, so let me erase some of stuff here. So we have this. So I'll erase this to give myself some room. Okay, so I'll write this up here. So nitrogen, we have 0.0296599 moles of nitrogen. Now I can take the grams that I have of nitrogen, subtract that from here. So I take 0.892124 grams, and I'm going to subtract out the 0.415447 grams. And that's going to end up with, when I subtract out the nitrogen, again, this is nitrogen plus oxygen. So when I subtract this out, I'll have just the oxygen. And when I do that, I get 0.4 0.4766, 0.4766, 0.47667 grams, and this is oxygen. So I have grams of oxygen here, and now I can use that, and I'm going to convert that to moles. So I have 0.476677 grams of oxygen. I'm going to multiply that by the molar mass. And which molar mass did I use? Yes, 15.9994 grams of oxygen on the bottom, 1 mole of oxygen on top. Grams cancels out. And when I calculate that out, I get 0.029, 0.029794 moles of oxygen. So here I have moles of nitrogen. I got the moles of oxygen from my original sample. And then here I have moles of the carbon and moles of the hydrogen from my original sample. So now, finally, now that I have moles, I can now use those moles to make my pseudo formula that's going to help me get my empirical formula. So let's go ahead and do that. So I'm going to erase everything that I don't need on the board. Okay. And now we're going to then, oops, we don't need the grams anymore. Okay, so notice I have, these are the moles. Now what I can do is I can write a pseudo formula using the moles. So this is where the subscripts come in. When you have an empirical formula, the subscripts are the moles. So what we're going to do is we're going to first write these down as subscripts in our formula. And so that's just going to be our starting pseudo formula. And then we're going to simplify it. So we'll start with carbon. So carbon has this many moles. So we're going to put 0.08929. And then hydrogen, so we can go ahead and erase this now. Don't need that. Hydrogen has this many moles, so we'll write that as a subscript, 0.208657. So we got that. We don't need that anymore. And then we have oxygen. Oxygen is going to have this as a subscript, so 0.0, oops. Sorry about that. 0.029794 moles. So we can get rid of that. And then finally, nitrogen. We'll write this as a subscript. So 0.02965999. Again, you don't need to carry all these numbers. You can cut it off after like 4 or 3. It'll run out the same way. And so now I have these as subscripts, but obviously this is not a good chemical formula because the subscripts are not in whole numbers. So we need to get the whole numbers, the lowest whole numbers possible. So we need everything with respect to 1. We need a ratio of all of these to 1. In order to do that, we need to divide by the smallest one. So if we divide by the smallest one, then that'll give us 1 for the smallest one, and then hopefully we get whole numbers from the others. So the smallest one is, well, we have 0.208 here, 0.029. Here we have 0.02965. Here we have 0.2979. So here we have 0.08. So it looks like nitrogen is the smallest one. So we'll go ahead and divide everything by this number here. And so we'll divide this one by 0.0296599. We'll divide this one by 0.0296599. And again, if you want to divide by 0.0296 or 2965, or you can do that. It won't matter. 0.0296599. 0.0296599. And so now you find the numbers. Obviously, this divided by this, it's the same number, so that's going to give us a 1 for the nitrogen. If you look here, these are really close together, so that's probably going to be really close to 1. And then this looks somewhat close. Well, they're off. It looks like maybe a factor of 10, less than that probably. So we divide these, and what do we get? When we get this becomes really close to 3. So that's going to be subscript 3. And that's going to be a 7. So this gets really close to 7. So this is going to be H7. And the other two are 1s. So this is a 1. This becomes a 1, like I said. That's really close to 1. So that's going to be a 1. And this is 1. So O-N. So then this, ladies and gentlemen, this, ladies and gentlemen, is the empirical formula for lysine. So that would be the answer to part A. Okay, so far so good. Excuse me. So what about the molecular formula? To find the molecular formula, it's really useful that they gave you the molar mass of the molecular formula. So this is the formula mass of the molecular formula. So what we know about empirical formulas and molecular formulas is that the difference in the subscripts between the molecular formula and the empirical formula are going to differ by a factor. It could be a factor of 2, a factor of 1, a factor of 3, whatever, but it's going to be some factor. If that is the case, then the masses are going to be differing by the same factor. So the formula masses of your empirical formula and the molecular formula will differ by the same factor. So if we know the formula masses for both the molecular formula and the empirical formula, we can find the ratio and find the factor from those that we need to multiply by. And then we can multiply these by that number, and that'll give us the molecular formula. So we need to calculate the formula mass for our empirical formula. And when we do that, we get 73.095. 73.095 grams per mole. So now all we need to do is take this number and divide it into this number, which is the molar mass of the molecular formula. So we take 150 grams per mole, divide that by 73.095 grams per mole. And when you divide these, you get approximately 2, or maybe exactly 2. So you get 2 as a factor. So this is really close to 2. So 2 is the factor by which your molecular formula and your empirical formula differ. So all we have to do now is multiply all the subscripts by 2, and we get the molecular formula. So 3 times 2 is 6. 7 times 2 is 14. 1 times 2 is 2, so this is going to be O2. And then 1 times 2 is 2, that's going to be N2. So here, ladies and gentlemen, we have the molecular formula for lysine. So here we have the empirical formula, here we have the molecular formula, and they differ by a factor of 2. And that, ladies and gentlemen, is how you do these sorts of problems. So I hope this was helpful. If you enjoyed the video, if this helped you in any way, then please, by all means, like the video, share the video, hit that like button. Also, make sure that you subscribe to my channel, hit that notification bell. When you do, make sure you click all so you'll be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question you need help with, if you have a topic you want me to cover, please put that down below. I would love to do that for you. Thanks for joining me, and have a great day.